Hello everyone, my name is Ashaya and my teammate Rokesh. We were students from Chanakya University and it's our privilege to present our research on the early prediction of heart diseases, specifically utilizing an XGboost and SMOTE enhanced machine learning pipeline. We were incredibly grateful to Professor J.B. Simha for their continuous support and mentorship on the endeavor. Cardiovascular diseases are a global health crisis demanding early and accurate predictions. This presentation introduces an XGboost and SMOTE enhanced machine learning pipeline. So, in this presentation, we are going to see the abstract, keywords, introduction, related works, methodology, exploratory data analysis, experiments and results, at the end, conclusion and the references. In abstraction part, we see heart disease continues to be a top cause of death globally, and early diagnosis is important. This paper describes a powerful machine learning process using Cleveland heart disease dataset with emphasis on effective pre-processing, class imbalance treatment via SMOTE, and classification via XGboost. Our model incorporates column transfer, data scaling, one-hot encoding, and XGboost hyperparameter turn for effective prediction. So, in the keyword we have taken heart disease prediction, XGboost, SMOTE, machine learning, Cleveland dataset, classification, and medical AI. So let's move on to the introduction to this paper. Heart diseases or cardiovascular diseases are a set of conditions impacting the heart and blood vessels. Coronary artery disease, heart failure, arrhythmia, heart diseases, and congenital heart defects are some of the heart diseases. Heart diseases are a major cause of death globally, causing millions of deaths annually. The main reasons are excessive blood pressure, smoking, diabetes, obesity, poor diet, insufficient exercise, and evolve because arthritis, a situation where a fat deposit in the arteries because blocked cutting of blood supply. Let's see some of the related ones. Machine learning models have been extensively investigated to make predictions of heart disease, and scientists have compared the different methods including logistic regression, support vector machines, decision trees, and ensemble based models including random forest. Potenker et al. Compared these models with a Cleveland dataset, highlighting pre-processing and data balancing for making correct predictions. Though earlier models such as logistic regression and SVM provide interpretability, ensemble-based models such as random forest and gradient boosting provide better accuracy and stability. Pottinger et al. Tested these models on the Cleveland dataset and highlighted the importance of pre-processing and data balancing in making robust predictions. Although logistic regression and SVM provide simplicity and interpretability, ensemble-based classifiers like random forest and gradient boosting are superior in accuracy and robustness. Let's see some of the methodologies like dataset description, data pre-processing, SMOTE for class imbalance, classification using XGboost. In dataset description, Cleveland heart disease dataset provides clinical information for 303 patients in features such as age, sex, type of chest pain, cholesterol, blood pressure, and so on. We converted original multi-class target into binary form like 0 as no heart disease and 1 as heart disease present. Data pre-processing. Pre-processing operations were applied using Skittin-Learn's pipeline and column transfer, which included imputation, encoding, and scaling. Numerical variables were standardized using standard scalar. SMOTE for class imbalance. To do with data imbalance, SMOTE was used. SMOTE creates synthetic minority class examples, result in an equally balanced training dataset and mitigation of majority class bias. Classification using XGboost. We selected XGboost because it is accurate, scalable, and has missing data handling built into it. Parameters like use label encoder equals false and evolve metric equals log loss were utilized to increase training efficiency. So let's see what is exploratory data analysis. EDA is an integral process in data science where data sets are analyzed and summarized to identify patterns, anomalies, hypothesis testing prior to the use of formal models. EDA assists data scientists in comprehending the relationships and structure of the data to make more informed decisions and apply more accurate models. Model construction pre-processed by model building. Here is the two analysis we have done. You can see that disease is more than no disease. Here also the cholesterol rate you can see it was earlier increased and then decreased and increased and decreasing. Here also two more analysis diagram you can see. For this more explanation about this exploratory data analysis, we can see in our next slide, which is presented by Yogesh.
Hello everyone, myself Yogesh. I will be doing the experiment and result section of our research on early prediction of heart disease. Here we have evolution metrics and performances analysis. In evolution metrics, we have employed several metrics of model performance, accuracy, precision, recall, F1 score, and confusion metrics. The dataset was divided into 80% training and 20% testing sets for following SMOTE application to the training set. Next, the performance analysis. The XGboost classifier produced the following performance on the test set. The accuracy we got is 84.78%, precision is 85%, recall is 75%, and the F1 score is 80%. The confusion metrics reported balanced classification of positive and negative classes. I will take you to the coding part and I will explain you the code and you will get to know there clearly. So let's move on to the coding part of our research paper. So here at starting we should import some libraries in Python to do the remaining part and to improve the model and to get the precision and other things what we have seen before. So we import pandas for data handling, seaborn and matplotlib for visualization, scikit-learn to ML tools, XGboost for classification, and SMOTE from imbalanced learn to balance our datasets. After importing the libraries, next is we load the dataset in the CSV format. Here we have loaded the dataset. Next, convert target to binary. Here we convert zeros to no disease and 1 to disease in our datasets. Drop columns with many missing values. We remove the irrelevant or incomplete columns like ID, num, that, etc. in the datasets. Next we do the separate features and target, separate features X and label Y, identify column types, separates numeric and categorical columns for specialized pre-processing pipelines. Numeric mean imputation plus scaling, categorical mode imputation plus one hot encoding. Next we do the combine preprocessor. Use column transformer to combine numeric and categorical pipelines. Apply preprocessing and split. Transforms the dataset using the combined pipeline. Now we balance the dataset using SMOTE. Generate synthetic samples for minority classes to fix data imbalance. Next we train a XGboost model. Train the classifier using logos as evaluation metrics. Next we predict and evaluate. So after this implementation, the accuracy we got for this model is 84.78%. I will now take you to the exploratory data analysis part. Same for this also, we should import some libraries and do the analysis part. Load the data set, convert target to binaries and zeros and ones, same. So here we do the exploratory data analysis. We set the plot style to white grid for clarity and choose a pastel color. Figure size to set to 12 into 10 inches for better visibility. First, in data exploratory, we are looking at target distribution. We use sns.countplot to visualize the distribution of the target variable. This tells us how many patients have heart disease versus those who don't. It helps us to detect class imbalance, which is later addressed using SMOTE. Next, we moving to the age distribution. We use sns.histplot with KD is equal to true to visualize how age is distributed across patients. This shows common age groups and help detect others or skewed data. At third, we have the cholesterol distribution. Similar to age, we visualize cholesterol levels to understand their spread and variability. Outliers can be identified and handled during pre-processing if needed. At last, we are doing a exploratory data analysis on chest pain versus target. We compare different chest pain types with the heart disease outcome using a grouped count plot. This helps us identify which types of chest pain are more strongly associated with the presence of heart disease. Finally, we plot light layout, avoids overlapping subplots, and plot.show display the visualization. These are the same code that we have implemented in the above section. So here we can see the accuracy, precision, recall, F1 score, support. Here we can see those things. I hope you guys have understood. So let's be moving to the next part, conclusion. This research suggests a scalable, accurate, and interpretable machine learning model for predicting early heart disease. This model utilizes pre-processing pipelines, SMOTE to balance classes, and XGboost to classify, resulting in excellent predictive performances and clinical ability. Further works can consider real-time integration and EHR systems and explainability dashboards for physicians. Our research offers a strong and flexible machine learning system for heart disease prediction that is both accurate and interpretable with the use of SMOTE for data balancing and XGboost for classification. The model is able to resolve data imbalance effectively while detecting patterns that basic models may not be able to do. The pre-processing pipeline ensures modularity and reproduc- reproducibility, making the method feasible for larger applications. So here are the references that we have took for this research paper. Thank you guys. Have a nice day.